Welcome to this concept explainer brought to you by CBSE ScoreLab of ProfSam.com.
Hello.
Today, we are going to master a very specific and very critical topic from Unit 3, Current Electricity.
Okay.
We are looking at resistivity of various materials.
Resistivity.
Yes, and before we even open the books, I want to make a promise to you.
Oh.
Today, we will move beyond just, memorizing values. Usually in school, what happens, students just mug up that copper is good and rubber is bad, and they move on.
That's very true.
We are not doing that. We will understand why copper conducts, but rubber does not. And we will master the microscopic formula that board examiners absolutely love to ask.
That sounds really useful.
By the end of this deep dive, you will never, ever confuse resistance and resistivity again. That is my guarantee.
I hope so. I have to admit, I always get a bit confused between resistance and resistivity. In my head, they sound so similar, I just, use them interchangeably sometimes.
It's a very common mistake, a very common one, but by the end of this session, that confusion will be gone.
Okay, I'm ready.
So let us start with a simple observation, something from everyday life. I want you to imagine a simple electric circuit.
Right.
Can you visualize a toaster in your kitchen?
Yes, of course. Making breakfast.
Good. Now imagine the setup.
Okay.
You have the cord, the wire plugged into the wall, and inside the toaster you have those heating coils that glow that bright red, right?
Right, the glowing part.
Okay. Now imagine we take a piece of copper wire, like the one in the cord, and a piece of nichrome wire, like the one inside the toaster.
Okay, copper and nichrome.
And imagine they have the exact same length and the exact same thickness.
Okay, so same length, same thickness.
And we connect both of them to the same battery.
Same battery source. Got it.
Here is the question. Why does the nichrome wire become red hot and glow while the copper wire just stays cool? Remember, physically, from the outside, they look like just two wires of the same size. Why does one behave so differently?
That's actually a very interesting question. I mean, usually we just think current flows and the machine works. We don't really ask why the material behaves differently.
Exactly.
I suppose. Is it because there's more, friction in the nichrome? Is it harder for the current to go through?
You are very, very close. But it's not just friction, rubbing your hands together.
Yeah.
It's about what is happening right inside the atoms. Specifically, it is about a massive difference in how the electrons struggle to move.
A struggle.
A huge struggle. And did you know that silver is actually the best conductor, even better than copper?
Really? Then why do we use copper for all our house wiring and everything?
It's simple. Cost. Just the cost. Silver is far too expensive.
Ah.
But copper is a very close second. But here is the fact that really shocks most students. Rubber is 10 to the power of 24 times less conductive than copper.
Wait, 10 to the power of 24? That's a huge number.
It's astronomical. I mean, it is the difference between a single grain of sand and maybe the size of our entire galaxy.
Wow.
That is how different these materials are. So to understand this massive gap, we have to look at the core idea.
Okay.
Resistivity is a material property.
Material property. What does that mean exactly?
It means it belongs to the substance itself. It tells us how difficult it is for charge to flow through a specific substance, regardless of its shape.
Regardless of its shape.
It doesn't matter if the wire is long or short, thick or thin. Resistivity belongs to the material's DNA, you could say.
So if I make a wire longer, its resistance changes, but its resistivity stays the same.
Precisely. Resistance is about the geometry. Resistivity is about the nature of the material itself.
Okay, that's a very important distinction.
To make this crystal clear, let's use an analogy. This is the best way to visualize it. I want you to imagine a large hallway or a corridor.
Okay, I'm imagining a hallway.
This hallway. This is our wire. Now imagine there are people trying to run through this hallway from one end to the other.
Right.
These people are the free electrons.
Okay, so the people running are the electrons carrying the current.
Correct. And in this hallway, there are pillars, or, big obstacles scattered everywhere. These are the lattice ions, the atoms of the metal that are fixed in place.
So the runners,
Yeah.
the electrons, have to dodge these pillars to get to the other side.
Exactly. Now, let us apply this to copper. Copper is a conductor. So imagine copper is like a very, very wide hallway, and it is packed with millions of people.
Millions of people.
Yes, a very high electron density. We denote this by the symbol N. But even though it's crowded with people, the arrangement of the pillars is very neat, very orderly.
So the traffic flows fast.
Very fast. The people can weave through easily. So lots of people. But a clear path, that means good flow.
Okay, high-end, easy movement, makes sense.
Correct. Now, consider nichrome. Nichrome is an alloy, a mix of nickel and chromium.
Right.
In our analogy, the hallway still has people running, but it's messy. It's filled with random pillars, debris, broken furniture, all over the place.
Why messy?
Because the atomic structure of an alloy is irregular. It's not a neat crystal.
Ah, so the people are constantly bumping into things.
Yes, they constantly collide and lose speed. And when they collide, they transfer their energy to the pillars, making the pillars vibrate.
And that vibration.
That vibration is what we feel as heat. That is why the toaster glows.
Ah, that makes perfect sense now. The struggle creates the heat. So what about rubber? Why is it an insulator?
Rubber is the really interesting one. For rubber, imagine the hallway is completely empty.
Empty. So no obstacles. That should be easy to run through.
No people. There are almost no free electrons to begin with.
Oh.
Even if the path is perfectly clear, there is no one there to run.
Wait, so let me get this straight. Is high resistivity caused by all the obstacles, or is it because there are no people?
That is the key question. And the answer is, it's both.
Both? How?
Yes. In metals, like our messy nichrome, the resistivity is high because of the collisions, the obstacles. But in insulators like rubber, the resistivity is enormous because of the lack of free carriers. There are no people to carry the current.
I see. So for metals, it's like a traffic jam problem.
Yes.
But for insulators, it's a ghost town problem.
You have nailed it. That is the perfect mental image. Traffic jam versus ghost town.
That's a great way to put it.
If you could look at a copper wire magnified 1 billion times, you'd see these red spheres, the nuclei in a lattice, and a blue sea of electrons just jiggling and drifting along.
I can picture that.
Resistivity is simply the measure of how much that lattice fights against that drift.
That's a very clear picture. The sea of electrons. It really helps to see it that way.
Good. Now, we must build the bridge to the textbook. We need to see how NCERT defines this, because that is what we need to write in the exam for full marks.
I have the text here. Section 3.7.
Excellent. Please read the definition that connects resistance and the dimensions of the wire.
Okay, it says, the resistance R is proportional to length L and inversely proportional to cross-sectional area A. Hence, R equals rho into L divided by A.
Correct. The famous formula R equals rho L by A.
And it continues, where the constant of proportionality. Rho depends on the material of the conductor, but not on its dimensions. Rho is called resistivity.
Let's unpack that carefully. If you double the length of a wire, the resistance doubles. Correct.
Yes, because the electrons have to travel further. It's twice as hard.
But the resistivity
stays the same.
It stays the same. It is the DNA of the material. Changing the length of the wire does not change the DNA of the copper atoms inside it.
Got it. So rho is constant for a given material at a given temperature.
Perfect. But the board examiners, they want more. They want the microscopic definition.
The microscopic one.
Yes. There is a formula that relates resistivity to the behavior of the electrons themselves. This is the formula that separates the toppers from the average students.
Oh.
Can you read that formula? It involves mass, m, and something called relaxation time.
Yes, I see it here. Equation 3.23 in some books says rho equals m divided by ne squared tau.
Yes. Rho equals m over ne squared tau.
This looks complicated. What are all these terms? It looks like a secret code.
Don't worry. We will break it down step by step. It's actually very logical. First, look at the numerator.
M is mass.
Mass of the electron. Is that a constant?
Yes. The mass of an electron doesn't change.
Correct. Now look at the denominator. E, the charge of the electron. Is that a constant?
Yes, that's also a constant. 1.6 into 10 to the power minus 19 coulombs.
So ME are constants. They don't decide why copper is different from rubber. The real heroes of this formula are the other two terms in the denominator, N and tau.
N and tau. Okay. What was N again?
N is the number density, the number of free electrons per unit volume.
Ah, the number of people in our hallway?
Exactly. If N is high, like in copper, you have millions of carriers. Now, since N is in the denominator, a large N means A.
A small resistivity.
Perfect. Big N means small rho. More people, better flow.
That makes sense.
Precisely. Now look at tau. This Greek symbol, tau, it is called relaxation time.
relaxation time? Does the electron, like, take a break?
In a way, it's the average time between two successive collisions.
Ah, so the time it spends running freely before it hits a pillar.
Correct. If the hallway has very few obstacles, like in a pure metal, you can run for a longer time before hitting something. So tau is large.
And if tau is large, since it's also in the denominator, resistivity is small.
You are catching up perfectly. So low resistivity comes from two things: having lots of carriers, a large N, or having very few collisions, a large tau.
And high resistivity means either you have almost no carriers, like in rubber with its small n, or you have constant collisions, like in nichrome, which would mean a small tau.
Exactly. That formula, the Framp D2 tau, is just the mathematical way of saying hallway with people and obstacles.
That makes it so much less scary when you explain it like that.
Before we move to an example, just a quick reminder, hope everything is clear so far. This concept explainer is from ProfSam.com. Now, let us try a simple comparison to lock this in. Let's compare copper and nichrome using their values. Copper has a resistivity of roughly 10 to the power 8.
10 to the minus 8.
Great.
Very small.
And nichrome is about 10^6 a meter.
So 10,006 is, wait, that's about 100 times larger than a tender after.
The actual value is closer to 60 times higher. But yes, you are right. It's much, much higher. Why?
Because nichrome is an alloy. Its structure is irregular.
The random pillars in the hallway.
Right.
Yes. That irregularity causes more scattering. More scattering means the electrons are hitting obstacles much more often. So what happens to tau, the relaxation time?
If they hit more often, the time between the hits becomes shorter. So tau decreases.
And if tau decreases?
Since it's in the denominator,
yeah,
a smaller tau means a bigger resistivity.
Perfect. You have just derived the physical reason for nichrome's high resistance. And by the way, this formula, this is the key to the next chapter topic. Temperature dependence.
Oh, how does that work?
Because when you heat a metal, the atoms vibrate more.
They become moving targets.
Exactly. And that changes tau. But we will save that for the next deep dive.
Okay, looking forward to that.
Now we need to talk about the silent killers.
Silent killers? That sounds dangerous.
They are dangerous for your marks. These are the small conceptual mistakes that students make all the time.
Oh, I definitely need to know these. I don't want to lose silly marks. What's the first one?
Misconception number 1. Resistivity depends on dimensions.
But we just said it doesn't.
I know, but under exam pressure, students see the formula Darrell Lawler's LAA. They think, oh, if I make the wire thinner, area A decreases, so maybe Ryle has to change to compensate.
Ah, I see the confusion. But that's wrong because R is the one that changes, not rho.
Correct. If you pull a wire to make it thinner and longer, its resistance goes way up. Its resistivity stays exactly the same.
Because it's still copper.
It's still copper. Remember, a siline only changes if you change the material itself or the temperature.
Material and temperature. Nothing else. I'll write that down.
Good. Misconception number 2 involves insulators. Students often write something like, insulators have high resistivity because the electrons move very slowly due to friction.
Wait, I think I saw that earlier. Is that wrong?
It is completely wrong. It is not about the speed.
It's not.
The real truth is, insulators have high resistivity because they have almost no free electrons. The value of N is practically 0.
The ghost town. It's not a traffic jam.
Yes, it's an empty road. There is simply no one there to carry the charge.
So let me just restate that to be sure. For insulators, the main problem is N being tiny. But for alloys like nichrome, the main problem is tau being tiny.
Exactly. You have caught the concept perfectly. If you write, insulators have high friction in the board exam, the examiner will cut marks.
Okay.
You must write, insulators have a negligible number density of free electrons.
Negligible number density. I will remember that phrase.
Now, to help you remember that big, scary formula, I have a memory anchor for you.
Please share. I always forget if N and tau go in the numerator or denominator.
Okay, remember the simple phrase, return equals mass divided by net time.
Return equals mass divided by net time.
Okay, let's break it down. Return sounds like rho.
Return. Rho.
Rho.
Got it.
Mass is simply m on top.
Mass.
And net time, NET, stands for NE tau.
Net time, NETNE tau. And since it's divided by net time, it's in the denominator.
Yes. Mass on top, net time on the bottom. Return equals mass by net time.
Also, you can use your hands. Visualize this in the exam hall.
Okay, I'm looking at my hands.
Spread your fingers wide apart. Wiggle them freely. This is copper. High in, easy flow of electrons.
Spreading fingers. Copper. Easy flow.
Now interlock your fingers very tight. Make a fist. Try to move them. You can't, right?
No, they're stuck.
This is an insulator, no free movement.
Locked fingers. Insulator. That's a good visual.
And finally, a simple rhyme to remember the numbers. Copper is for flow, $10. The atrom, it's for glow, and rubber is for no-go. Flow, glow, no-go. I like that. The powers of 10 really show the huge difference.
They certainly do. So, let us summarize everything we have learned today in 3 quick exam-safe points. Point 1. Resistivity, rho, is an intrinsic property of the material. It is independent of its length or cross-sectional area.
Independent of dimensions. Check.
Point 2. The microscopic formula is rho Na2 tau. So resistivity depends inversely on the electron number density, N, and the relaxation time, tau.
Return equals mass by net time. Check.
And point 3.
Yeah.
Metals have low resistivity because of a very high N. Insulators have huge resistivity because of a negligible N, and alloys have higher resistivity than pure metals because of a lower tau due to more collisions.
That covers everything perfectly.
It does. And remember, if you can just visualize that hallway, the people and the pillars, you can answer any conceptual question the board throws at you.
I feel much more confident about this now. It's not just some random Greek letter anymore.
That is the goal. Understanding the physics makes the math easy. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is PROF Sam.
Yes, ProfSam.com. Keep learning, and we'll see you in the next deep dive.